So I've been talking a lot about linear algebra stuff. This is a bit weird. I'm a topologist, not an algebraist. And in keeping with that, not what I actually specialize in kind of approach here, I decided that I would say something about abstract group theory. And one of the reasons I want to talk about group theory in particular is because this is a subject that I think a lot of people can understand the basics of it. It gives you a really good illustration of how abstraction in mathematics can be a powerful tool, and yet it's something that people don't really learn about usually until junior or senior year of undergraduate at the earliest. So it's a bit weird. It's actually not a super complicated concept, but for some reason people don't learn about it. Now, I am going to tell you very briefly what is a group, but I then want to kind of step back, and instead of focusing on examples of groups from the start, I'm going to start looking at some objects, and we'll see how they have these properties of being groups. And this will kind of show us, that's why those properties were chosen by mathematicians as useful properties for this abstract concept. So first of all, we're going to answer this question. What is a group? Well, a group is a set G with a binary operation taking G cross G to itself, and we usually write this operation with a star or a dot or something, but in practice you usually drop the operation and you just write elements next to each other, and it's implied that the operation is done to the pairs of elements that are next to each other. Now, one requirement here is that this operation is associative. In other words, this means that A star B star C is equal to A star B star C. And this is why we can drop the operation and just write A, B, C, and this is unambiguous, because the point is, it doesn't matter if we do the operation between A and B first, or if we do the operation between B and C first, we will get the same answer either way. So we can write this unambiguously. And that saves us from having to write the actual operator in between the elements, and it saves us from having to write a bunch of parentheses. And as you may or may not know, mathematicians are kind of lazy a lot of the times. We love to save time and make our writing more concise. So we like to do this. Now, it's not just that we have this associative operation here. We have some other properties for it as well. We say there exists an element E in G such that for all little g in G, EG is equal to E. We also say that for all little g in G, there exists a G inverse in G, such that G inverse G is equal to E. This E is called the identity of the group G. And sometimes you'll see it written as 1, sometimes you'll see it written as ID, often it is written as E. In some rare instances, well, I shouldn't say rare, in some special cases you might see it written as 0, but that's kind of for something called abelian groups, in which this operation is not just associative, but also commutative. And then this is called the inverse element. So the inverse element means essentially that everything in G, there's something that when you use this operation on that pair, you get back to the identity. Now, a lot of things turn out to be groups. By the way, you can show from these properties that, why did I say EG equals E? I meant EG equals G. I'm an idiot. So you can show from these properties that the identity holds good on both sides. So G times E is also equal to G, and you can show that the inverse works on both sides as well. But why would you think of these properties as something that are interesting to study? Well, the answer comes down to the behavior, really, of functions. In a lot of ways, what we have just described encapsulates the behavior of functions from a set to itself that are bijective. And in particular, it encapsulates the behavior of some subset of those functions which preserves some kind of structure that we give to the set. So for example, if I just have a set X, let's define F to be the set of bijections from X to itself. Now there's a few things to notice about this, but the main thing that I want to point out here is that F is a group with the operation given by composition. And how can we see that that is the case? Well, let's think for a minute about how these functions in F behave. The first thing that we can notice is that the identity map is an element of F. Remember that the identity map takes X to itself and it just sends any element here to itself. It's the identity function because whatever you give it, it gives you right back, identical to whatever you gave it. So that is definitely going to be a bijection from the set to itself. And the nice thing about this identity function is that for any function little f in F, the identity composed with F is equal to F composed with the identity, and it's still equal to F. Obviously, if this function doesn't change anything in X, then it doesn't matter if we use it like this. The other thing to notice here is that because these are bijections, they admit inverses. But F is supposed to include all of these bijections, and the inverses are bijections themselves. So what we can say is that for all little f in capital F, F inverse is in F, and here I'm using F inverse to indicate the usual inverse for a bijective function, and we get the property that F inverse composed with F is equal to F composed with F inverse, and it is equal to the identity function on the set X. So actually, the group structure encapsulates how these bijective functions behave. But it turns out that we can do better than this. It turns out that they actually encapsulate more than just bijective functions from a set to itself. By the way, this set F with operation given by composition, this is usually called the symmetric group on X, and you might see it written as symmetric group on X, or you might see some other notations. Again, I am not an algebraist, so I don't really need to deal with this stuff too much. I'm sure algebraists have a ton of their own clever notations for these things. But one of the nice points about groups is that they also encapsulate the behavior of a lot of stuff that isn't just all the bijective functions. We can do things like we can say, what if we want to consider just bijective functions which preserve some special structures on our set X? So maybe instead of taking just a set, let's suppose that V is a vector space. And I want to say, I'm going to define GL of V to be the set of linear operators T from V to itself that are invertible. I can't spell invertible apparently, but there we go. So all the linear maps from a vector space to itself that are invertible. And I claim that this is a group under composition. And it's actually not too difficult to show that this is a group. Because remember, these are linear operators. They're basically functions from V to itself. Because they're invertible, that means that they're bijective. So everything that I said about bijective functions from V to itself applies to these as well. The only thing to verify is that when we take composition of two linear operators, we get another linear operator. That's almost immediate. I mean, we know that's how linear operators behave. You compose two of them, you get another linear operator. It's very, very short to show that fact. The other thing that we have to show is that T inverse is linear. And again, that is not too difficult to do. So we need to show that T inverse is linear, and we need to show that T1 composed with T2 is also linear. And then, from what we said before about composition of functions, it becomes clear that this is a group. This is called the general linear group of V. And it turns out that these are really important types of groups. So, the thing to notice here is that we're dealing with bijective functions, and these bijective functions are preserving some kind of a structure on V. In fact, we could go further than this. A lot of the most interesting groups came from starting with looking at, well, I should say a lot of the original sort of study of group theory came from looking at objects and asking ourselves, what are the maps that preserve this object? So a good example would be, what if I started off with, let's say, a triangle in the plane, and I asked myself, what are the different transformations of the plane which preserve distances in the plane and also map this triangle to itself? So, maps from R2, the plane, to R2, preserving distances and sending, let's give this some labels, ABC, sending the triangle ABC to itself. Well, if you think about it for a little bit, there's only a couple of things that we can do here that will take this triangle back to itself. Basically, I can rotate the triangle, so I can take these vertices. Imagine here that this is, these are all the same length here. So if that is true, then I could rotate this, so I could send this around so that now C is at the top, A is over here at the left, and B is over here. This would be a 1/3 rotation. I could give it a 2/3 rotation, which would take C all the way to the left, and it would bump the other two vertices along with it. I could leave it well enough alone. I could just do the identity transformation on the plane, which leaves all the points fixed. That would certainly be valid. The other thing that I could do is I could do a reflection, say, along this line. So if I did that reflection, then that would leave the top vertex where it is. So A would remain here, but C would now be on the left, and B would be on the right. So this is the flipping this way. And in addition to flipping this way, I could flip it along these two lines as well. It turns out, if you look at all the definitions of a group, this is also a group. And this is one of the reasons why people started getting interested in groups, because it turns out that if you look at transformations that preserve some nice properties of a set, they pretty much are always going to form a group. Assuming that we're talking about like reasonable properties of the set to talk about, some reasonable structure on the set, then the functions that preserve that structure, if you compose them together, they still preserve the structure. Assuming that this structure doesn't allow you to collapse the set in any way, so in other words, as long as you have to have bijections from the set to itself, then they will be invertible. And since you preserve the structure going one way, you preserve it coming back. And because of that, you will always end up with a group. In fact, every single group arises as a subgroup, in other words, a subset of a group that is itself a group, so closed under the binary operation. It arises as the subset of some symmetric group. So this is a theorem. I don't remember who this theorem is originally due to, but every group G is a subgroup of the symmetric group of the underlying set of G. Now, I'm just going to write that as the symmetric group of G. One thing that you should be careful of when you're talking about this stuff, strictly to talk about the group G, I should say, here's the set and here's the operation. But we often kind of gloss over the operation because the operation is usually implied. And for this reason, we often just give the same name to the set and to the group. But the group, strictly speaking, requires us to have both a set and an operation picked out. So why is this true? Well, the point is that for all little g in G, we can define fg, taking G to itself, by fg of x is equal to G times x. And then we show that the set of fg, or all these functions, form an identical group to G. Now, by identical here, we mean isomorphic, which I haven't really talked about. But anyway, this is the basic idea behind group theory. This is where it comes from. You're thinking about bijective functions from a set to itself that preserve some kind of structure on that set. And all of those properties, those kind of funny abstract properties that we talked about back at the beginning to define a group, well, they just describe the basic properties of these bijective functions. The other thing to notice here that I want to mention really quickly is that this operation does not have to be commutative. And it's really quite simple to see that it doesn't have to be commutative because function composition does not in general commute. So in other words, since f composed with G is not necessarily G composed with F, we note that the group operation need not commute. Now, if you want an explicit example of this, think back to the linear operator example. It's pretty easy to come up with two linear operators whose composition does not commute. Remember, composing linear operators is the same as multiplying their matrices, and we know that matrix multiplication is not commutative. So that general linear group that I mentioned before will usually not be commutative unless we're dealing with like a one-dimensional vector space or something. All right, so that was a very quick sort of sketch of why group theory is of interest to mathematicians. I feel like it was not a particularly great introduction if you want to know the technical details, but hopefully it kind of shows you this is what mathematicians do. We sort of look at some things and then we say, hey, look, there are some nice properties of these things which we can sort of abstract away. And the power behind this is if you can solve one problem using a certain method, maybe you can solve more problems using that method as well. And maybe it's because all that you really used to solve it were a few basic properties. And if you were to just kind of ignore all of the superfluous details of your particular problem, you would now have a general method for solving all problems that have these few basic properties. And that's what you're doing with group theory. You can start off by thinking about, well, what are all the different things that we could do to this triangle in the plane to get it back to its original position, but maybe we've scrambled things around. And then you could start asking similar questions. Well, what if we used a square instead of a triangle? What if we used a hexagon? And so on. But eventually you realize that you're doing a lot of the same stuff in every one of these cases. And really, all that it boils down to are those very basic properties that we talked about back at the beginning as defining a group. So if you are really interested in understanding more about groups and those kinds of things, I might talk more about them at some point, but there are plenty of resources online that you can go to that will give you a nice basic introduction. What I don't think a lot of them necessarily do is they don't necessarily explain why would somebody have thought of these abstract properties in the first place? What motivated people to say, hey, this is something that's of interest to us? And that is kind of what I wanted to illustrate here. Why did people get interested in these properties that became known as a group?